Sketch the graph of the function f of x whose derivative is f prime of x equals x minus 1 squared times x minus 2. To sketch the graph of f, ideally we would need the information from the function f, the first derivative f prime, and the second derivative f double prime. The function f will tell us how high or low the points are. The first derivative will give us the interval where the function is increasing or decreasing. From the first derivative, we can differentiate it to obtain the second derivative. The second derivative will tell us the interval where the function is concave up, concave down, or any inflection point. Although in this case, we do not have the given function f of x, but we have the first derivative, so we will be able to find the intervals where the function is increasing, decreasing, concave up, concave down. Also, we can find the location of the local min, local max, and the inflection points, although we don't know how high they are or low, but we know exactly where they are on the x-axis. First, we set derivative equal to 0 to find the critical points. This will be the cut points when we construct the sign charts as well. Set f prime equal to 0. This product is 0, so each of the factor can be 0. We set each of the factor equal to 0 and solve for x. We see that x equals 1 and x equals 2. These are the critical numbers as well as the cut points. For the second derivative, we use the product rule. The derivative of the first factor, 2 times x minus 1 times the second factor, x minus 2, plus the first factor, x minus 1 squared, times the derivative of the second factor, which is 1. And then we simplify this. This is 2 times x minus 1 times x minus 2 plus x minus 1 squared, and we factor out x minus 1. In the first term, we still have 2 times x minus 2, and the second term, we have x minus 1 left. This is x minus 1 times 2x minus 4 plus x minus 1. So this is x minus 1 times 3x minus 5. And the derivative is 0 when each of the factor equal to 0, or when x equals 1 and 3x minus 5 equals 0, or x equals 5 over 3. These are not the critical numbers, but they are cut points. We then construct the sign chart for f prime using the critical numbers at cut points. They are 1 and 2. When x equals 1, f prime is 0, and when x equals 2, f prime is 0. These are the only two zeros for f prime. We then test the sign of f prime in each of these subintervals by picking any test point in each of the subinterval. From negative infinity to 1, we might pick 0, and we plug 0 into the first derivative. We see that 0 minus 1 squared is always positive, 0 minus 2 is negative. The sign at one particular number in each interval determines the sign of the entire subinterval. Since f prime of 0 is negative, f prime is negative on the entire interval where 0 comes from. From x equal 1 to x equal 2, we picked 1.5 for example, and we plug this into f prime. Remember, the square factor is always positive, and so we can ignore it. If we plug in 1.5 into x minus 2, 1.5 minus 2 is negative, so f prime is negative on the entire subinterval. From 2 to infinity, we pick any number, 3 for example, and we plug it into the first derivative. 3 minus 2 is positive, So f prime is positive from 2 to infinity. We see that the function is decreasing from negative infinity to 1, decreasing again from 1 to 2, and then increasing from 2 to infinity. For f double prime, the cut points are x equals 1 and 5 over 3. 5 over 3 is not quite 2 yet, but it is between 1 and 2. We then pick any number in each of the subinterval to test the sign of f double prime. F double prime, after we simplify this or factored it, we have f double prime equals x minus 1 times 3x minus 5. When testing the sign of the first and the second derivative, it is better to use factor form. If we plug in any number between negative infinity to 1, 0, for example, we see that for f double prime, 0 minus 1 is negative, 3 times 0 minus 5 is negative, a negative times a negative is positive. So f double prime is positive on the entire subinterval. From 1 to 5 over 3, 5 over 3 is more than 1 and less than 2. It is also more than 1.5. So we would pick 1.5 in the interval from 1 to 5 over 3. If we plug in 1.5, we see that 1.5 minus 1 is positive. 3 times 1.5 is 4.5 minus 5, which is negative. A positive times a negative is negative. So f double prime is negative on the entire subinterval. And after 5 over 3, we can pick any number in this subinterval, 100 for example. 100 minus 1 times 3 times 100 minus 5, a positive times a positive is positive. So we see that from negative infinity to 1, the function is concave up. From 1 to 5 over 3, the graph concave down. And from 5 over 3 to infinity is concave up again. To determine the shape of the graph, we would combine all of these cut points. There are 3 distinct cut points from f prime and f double prime. They are 1, 5 over 3 to 2 in increasing order. From negative infinity to 1, we see that the graph is decreasing and concave up. From 1 to 5 over 3, the graph is decreasing and concave down. From 5 over 3 to 2, the graph is decreasing and concave up. And from 2 to infinity, the graph is increasing and concave up. We now put this shape and form the graph. But in this case, we won't be able to use a y-coordinate because we were not given the function f of x, so we don't know how high or low the graph is. But we can use the x-axis to determine the location of the special feature of the graph, such as the interval where the function is increasing, decreasing, concave up, concave down. On the left-hand side of 1, from negative infinity to 1, the graph is decreasing and concave up. We don't know how high or low the graph is, so we don't know the exact graph, but as long as we have decreasing and concave up, then it satisfies the given condition. From 1 to 5 over 3, the function is decreasing and concave down. As long as we have clear decreasing and concave down shape in that interval, then we are good to go. From 5 over 3 to 2, the graph is decreasing and concave up again. As long as we have a clear shape of the graph in such interval, then it is okay. From 2 to infinity, the function is increasing and concave up. We emphasize that in this case, the graph is not unique because we don't know how high and how low these points are. We have an inflection point at x equals 1 because the second derivative changes its sign there, but we don't know how high it is. We have another inflection point at x equals 5/3. We also have the local minimum at x equals 2 because the function is decreasing and then increasing, but we don't know how low it is.